we defined last time, we started this really simplicial complex, and we, if I remember correctly, we stopped when we calculated. Let's make a recall. What the notation? We're looking to find a field FQ. V is FQ to the n, and we took the simplicial complex such that the vertices, or if you want x0, is all non-trivial. Non-trivial means neither 0 nor v subspaces of V. There are too many V's. This would be V, the space. And we have a tau function, which is a type function from such W. So the tau of W is simply the dimension of W. And Xi, the I simplices, is simply all the sets Wi1 inside Wi0 inside Wi1 inside W of J0, J1, sorry, up to Ji, right? Like a flag of I plus 1 subspaces is the set of I cells, and we started to calculate. So we saw that and we call this X, say it is the spherical NQ. Okay, this is the flag, and what we saw that S3Q is a bipartite graph, bipartite Q plus 1 regular graph, which is the points versus lines of projective plane, of the projective plane over FQ. And the eigenvalues in this case were plus minus Q plus 1, and plus each one of them with one multiplicity, and plus minus square root of Q, each one with very high multiplicity, which we basically can calculate. Now the first really interesting and not completely trivial case is the next one. So let's look. I want to compute it. I hope that already today you will understand why the computation of these eigenvalues is important for us. So let's look at S4Q. So S4Q now, this is the one-dimensional, two-dimensional, and three-dimensional. Now we have three levels. So this is a two-dimensional complex, right? The maximal chambers are of length 3, and it gives rise to three bipartite graphs. The bipartite graph that B12, B13, and B23. So this is 1 against 2, this is 2 against 3, which means the subspaces of dimension 1 against the subspaces of dimension 2. And like actually, yeah, I'm going to compute this, even though there will be, later on we'll need a different interpretation, but I'm sorry, yeah, okay. I prepared this, I didn't think, now I see that if I would look ahead. Okay, they're also relevant, let me do it anyway. And then we'll look at various other, they're like to every part, one of the way to analyze simplices in many cases is to reduce the problem to graph. And we develop a little bit of machinery of evaluating, of studying mixing properties of bipartite graph, which are biregular, right? That's what we developed in the previous weeks. So let's look at them. They are relevant. And here, the problems are not always completely trivial. Let's look first at B13, so one-dimensional spaces versus three-dimensional spaces. So let's study these two graphs. Now, in this case, the graphs is a bipartite regular graph. The degree is the same, right? And that's not difficult to compute. The number of points we have here, this is the one-dimensional spaces. We have cube to the 4 minus 1 divided by q minus 1, what we call n 4 over 1 cube. This is the number of subspaces, right? And here we have the three-dimensional, which is by symmetry, it's the same thing. It's 4 over 3, but it's exactly the same size. And the question is, what's the degree from here to here? It's really the question, how many, given a one-dimensional space in the four-dimensional space, how many three-dimensional space containing it? But given a one-dimensional space, the number of three-dimensional spaces containing it is exactly as the number of two-dimensional spaces in a three-dimensional space, because we can look at the quotient. So the degree here is exactly what we call 3 over 2, which is really 3 over 1 q. Okay, the number of two-dimensional spaces here. And here it will be the number of one-dimensional, so it's exactly the same. And now, if you want to look at the matrix, if A is the adjacency matrix of this graph B13, then B13, then let's, so we think of it as Z, it's a bipartite, so there is nothing here, and here we have some matrix B, and here we have some matrix BT. Right? That's exactly the kind of thing we did last time. And then here we see that, okay, so A squared is BT, here is BTB, 0, 0. And we want to compute the eigenvalues. Now, the eigenvalues of, okay, so let's see now what is BBT. So, or BTB, it doesn't matter. So we said that this is the A square is the adjacency matrix of the graph on the same vertices, representing going by paths of length 2. So I go from a vertex to some vertex and go to some other vertex. It can be maybe going back, and going back will be done in this number 3 over 2 or 3 over 1 cube times an identity, plus, now let's see in how many ways I can go from one to another. So if I have a subspace W1, and here I have W1 prime, both of them are of dimension 1, so they are contained in some two-dimensional space here, a unique one which contains both of them. And the number of paths I have here is exactly the number of three-dimensional spaces containing this specific two-dimensional space. Right? Is it clear? I want to ask myself in how many ways I can go from a one-dimensional space to a three-dimensional space and come back to a one-dimensional space. So this is really going from a one-dimensional space to some three-dimensional space containing W1, and also containing W1 prime. And they are different than each other, which means that, that this three-dimensional space must contain the two-dimensional space spanned by this one and this one. Okay? So given this and this, it gives me some vector space of dimension 2 here. Let's call it U. And the question is, how many three-dimensional spaces containing it? And that's very easy. This is exactly Q plus 1. Because we are inside a four-dimensional space. So the number of three-dimensional spaces containing a given two-dimensional space inside a four-dimensional space is exactly Q plus 1. Is it clear? I mean, these are easy considerations. Somehow you have to do it yourself once in a lifetime, somehow to get used to that. So this will be plus Q plus 1 J, J minus I, where J is the all I formula, right? So now let's do this computation once again. We did this kind of computation last time, but let's do it again to see what the numbers are coming here. So this is equal, so BBT is equal to Q to the, Q to the, so this is Q minus 1 divided by Q minus 1 times the identity. Okay, maybe let's write it better. As Q squared plus Q plus 1 times the identity plus Q minus I, Q plus 1, J minus I. So we take the J minus I there, so we are getting Q square I plus Q plus 1J. And now you remember we said, okay, so it means, let's see how B acts. So J acts as 0. We decompose the space. See, this is like, PBT is like looking on one side. I'm just looking on this side, right? BTB will be starting from here, but the eigenvalues will be just the same. Well, anyway, we know this is a linear algebra exercise, which I showed you or gave you as an exercise in one of the lectures before, that BBT and BTB always have the same eigenvalues. Maybe they are different by zeros. Well, in this case, I think they are even not different because this is both of them are of the same size. If they are not of the same size, then there might be some zeros in one of them which not in the other. So, okay, so what we have here now, so we have functions on that side of the graph which sum up to 0. The function which sum up to 0, the orthogonal complement of the constant, are vanished by J, right? J is 0 on these functions. So basically what we know that on that space in which J vanished, only this acts as Q squared. So the eigenvalues, most of the eigenvalues of A squared will be Q squared, which means that the eigenvalues of A will be, many of them will be plus or minus Q. Because Q squared will be an eigenvalue of J. Right, I'm doing it now faster than last time. I don't want to do in each computation, so all the details. Is it clear? But start me if it's not clear. And now what will be the largest eigenvalue? We can guess. What should be the largest eigenvalue? Exactly the degree. Right? But let's see, let's be on the safe side and let's see that indeed that's what we get. Because you see, on constant functions, this is what we get on functions which sum up to 0. On the constant function, we'll get from here Q squared plus Q plus 1, the size of f. The size of J, right? If you take a constant function and you multiply it by 1, 1, 1, 1, 1, 1, 1, and you take 1, 1, 1, what you get is exactly as an eigenvalue the size of J. the size of J here is the size of this side of the graph, which is q to the 4 minus 1 divided by q minus 1. So this is equal q squared plus q plus 1, q to the 4 minus 1 divided by q minus 1. And what is the outcome? What should be the result? Don't compute. You should know.
Q squared plus Q plus 1.
It's q squared plus q plus 1 squared. Because this should be an eigenvalue not of A, but of A squared. Right? As an eigenvalue of A, I'm going to get the degree. But as an eigenvalue of A squared, I'm going to get the degree squared. Right? So this should be checked. At least regarding the degrees, it sounds correct, but you should hope that this is correct. I checked it. But I won't do it now. Better to be on the safe side. Okay, so let's do the more interesting and slightly more difficult case, just to show you what happens because so far we didn't see really, and I have a point, but I want to do one more example in details because I want I had a very nice success last time. I gave you a good exercise and three of you answered me. Two of them only last night and this morning, so I didn't have time to read it, but the one who sent me the first and supposed to, yeah, but you will present it soon. And so I'll give you a more difficult exercise now today, but let me first point out something which is let me do one computation. Okay, and this is the G12. Okay, so now G12, okay, my notes I call it G12, okay, let's say B12. So this is the one-dimensional against the two-dimensional. Now there are many more two-dimensional spaces than one-dimensional spaces. So this time is the first time that we see an interesting example of a bipartite graph, which is biregular, but really biregular, like the degrees are different. So let's see how many we have here. That's we already computed. The number of them is 4 over 1 cube, which is approximately q cube. And here we have 4 over 2 cube. Now, what is 4 over 2? That just, I don't remember if we did it last time or not, but think about it. How many subspaces you have of dimension 2? So you choose, you have for the first, you take a basis for such a vector space. So for the first vector, you have q to the 4 minus 1 possibilities. For the second basis element, you have q to the 4 minus q. And now, and this will give you all the independent sets of size 2. But many of them define the same vector space of dimension 2. How many vector spaces of dimension 2, given a vector space of dimension 2, how many bases it has? I have to divide this by q squared minus 1 by q squared minus q. Now this is not difficult to compute. It's q squared plus 1. The q goes out, and we get here q to the q minus 1 divided by q minus 1. So this is q squared plus 1 times q squared plus q plus 1. So this is approximately q to the 4th. So we see q squared plus 1 times q squared plus q plus 1. So you see that this is an unbalance, because this is something of order approximately q cubed, and this is something of order approximately q to the 4. Now let's see what is the degrees here and what the degrees in this side. So the degree here is given a vector space of dimension 1, how many vector spaces it has of dimension, how many vector spaces of dimension 2 containing are there, which contains that one. Which contains that one, right? This is the degree, how many two-dimensional spaces we have which contain a given W of dimension 1. So this is exactly as the number of one-dimensional spaces of the quotient. So this is the degree is 3 over 1 q, which is approximately q cubed. And on the other end, given a two-dimensional space, how many one-dimensional space are containing in it is exactly q plus 1. Okay? And that's okay, that's more or less what we expect, because what should happen is that the number of vertices on this side times the degree, what? The q. The number of vector space, the number of vertices on the left-hand side times the degree should be equal to the number of vertices on the right-hand side times their degree. So here we have something like q to the 4th times q, this is q to the 5th, and here we have q to the cube times q to the square, also q to the 5th. And in fact, they must be equal, not just approximately equal. So if you want, we can get an identity, really. The identity should say that 4 over 1 q times 3 over 1 q, which is is really equal to 4 over 2q times 2 over 1q. Must be true. Again, I don't check. It must be true, right? It's really nice identity. Okay. So this is the graph. But now let's understand. Now this time it's slightly more interesting story, because here we really get that you see the left-hand side is much smaller than the right-hand side. So this time we really have this is the other way. What? The other way around. Right? So it should be. Yeah. Right. So here we have B and here we have BT, and they are really of different, not square matrices, but the eigenvalues of BT, say union, whoever you want to be, BTB, they can differ from each other only by zeros, and 0 is a great eigenvalue. No, it satisfies all the good conditions. It's a very small number, 0. In absolute value, it's still very small. Especially in absolute value. But let's see what are the other eigenvalues. So it's enough to compute just one of them. So let's compute. Okay, so let's see. What will be like the going from the left side to the right side and coming back. So here we will go from a one-dimensional to two-dimensional and come back. So like the BVT will be the degree, right? Like the number of time to go and come back is the degree here, which is 3 by 1 q, the identity. And now the question is, in how many ways we can go from one dimension to two dimension and come back. That's actually easy. And this is plus, there is a unique way, plus j minus I. Okay, good. That's easy, and yeah, but I have a point I want to show something here. Okay, that's easy. So this is equal, so let's write it down. So this is equal, I'm continuing here, so this is q squared plus q plus 1 I plus j minus I, so this is q squared plus q I plus j. And again, so what are the eigenvalues? The eigenvalues will be the main j vanish on the functions which, I always think of vector as function, right? As a vector as function on the vertices. So it vanishes on the functions which sum up to 0 on this side, right? And the only thing which continue to live there is, so the eigenvalues are the square root of this, is the square root of q squared plus q, plus minus, and the trivial eigenvalues. What are the trivial eigenvalues? Now, let's see if you remember what we studied last time. What is the trivial eigenvalue now?
Plus minus degree.
What?
Plus minus degree.
But what's the degree? There are 2 degrees. You already forgot? If we have a bipartite, biregular graph, where the degree are k and l. So what is the trivial eigenvalues? Square root of k times l. Very important. Square root of k times l. Right? So it will be square root of k times l, and then plus and minus. So it will be plus and minus. Okay, let me put more space here because we need more space. It will be, eigenvalues will be plus minus square root of what? Let's write precisely. The degree of one side times the degree of the other side. What is the degree of one side? Is 3 over 1. 3 over 1 is q squared plus q plus 1, right? Is the number of subspaces of dimension 1 inside dimension 2, so this is 3 over 1 q, right? This is the degree from the left hand side, times the degree of the right hand side. So this is the eigenvalue. And 0 will come up. Okay, 0 will come up. If it won't come up on that side, on the small side, it's certainly going to come up on the other side. Why? Because it must come, right? If you remember the lemma, did I prove it or just gave it as an exercise? What?
You did prove it.
I did prove it, and from the proof you can see that really there are zeros coming up to the game if the sides are not the same. Somehow you have a map from small space to a bigger space and going back, and things which are not in the image, I think, are going to 0 in the kernel or something. The zeros certainly come into the game. So 0 will come up to the game. Anyway, okay, now, so this is, okay, let's see. So this is q cubed square root. So this is approximately q to the 3 over 2. And this is approximately q. Alright? Now, are these Ramanujan graphs? You remember, I gave the definition of Ramanujan, right? Did I define Ramanujan graph in the previous class? I planned to, right? Did I?
You discussed it, but what does it mean in Ramanujan in biregular?
Right, very good. So I defined Ramanujan graph only for k-regular graph. And for k-regular graph, Ramanujan graph was the second if the largest eigenvalue, like the k-regular graph, the largest eigenvalue is k. The second to largest should be not less than 2 square root of k minus 1. So you might say, well, maybe that should be the general definition of Ramanujan. Like, take the largest eigenvalue and take the square root of it. K minus or whatever. And then If this would be the definition, then these are not Ramanujan. Because here the largest eigenvalue is something like that. The second largest is q. If I take square root of this, I'm getting q to the 3/4. And this is bigger. But this is not the right definition. So let me give, that's an opportunity. I did a computation in some sense in order to enable me to explain you what is the right definition of Ramanujan bipartite graph. And this is the preparation for us to the notion of Ramanujan complexes in the higher dimensional case to understand where the notion comes from. I will not prove what I'm saying now, but well, because I didn't really prove also the Lombopana. At some point maybe we will prove the general Lombopana, which will include all of them, so I don't want to do it in too many special cases. So let me explain. So recall that K regular graph is a finite K regular graph. Say connected, finite connected K regular graph is called Ramanujan if every eigenvalue of it always mean of its adjacency matrix satisfies lambda either plus or minus k, or lambda is at most 2 square root of k minus 1. Where this number 2 square root of k minus 1 come from? So such, let's call it x. Such x is covered by in the sense of algebraic topology, the universal covering of x is covered by the k regular tree tk, which is this is an infinite tree, such that the degree of every vertex is exactly k. And you know, it goes forever. And this is the universal cover space of a k regular tree. Now, what is A? What is the adjacency matrix of the tree? So we can really write x as tk divided by gamma, where gamma is really pi1 of x, the fundamental group of x acting on tk. Right? I hope everyone is familiar with basic algebraic topology, right? That's the kind of thing. If you have a topological space, you can talk about its universal cover. In this case, universal cover is exactly 3. And now here one can really build it by hand. You don't need fancy algebraic topology. You can really kind of define it by elementary means somehow to show what to talk about that. But now, but here's the point. Look at the operator A from L2 of tk to L2 of tk, which defines by, so L2 of tk means functions L2 on the vertices. So these are functions, like complex functions, such that the sum over the vertices square is finite. Right? So this is an this is like an operator between two Hilbert from an Hilbert space to itself, and I can talk about its spectrum. And the spectrum of this operator, so this is a non-trivial exercise. I mean, you have to know a little bit about the theory. One can do it combinatorially after one understands the meaning of this. But at this point, I don't want to worry about that. I mean, I'm just telling you this is a story in order that you will understand why I'm going to define differently than you expect the Ramanujan for bipart, right? The spectrum of this is minus 2 square root of k minus 1 to 2 square root of k minus 1.
You normalize?
What?
You normalize the...
No, I didn't normalize. I mean, I could, but I didn't, so let's not normalize. This is the spectrum. So, now, okay, this is the spectrum of this. Okay. Now, what is now the definition of Ramanujan graph? Basically, the way you should really think about the definition of Ramanujan graph is in the following way. We have the universal tree. The universal tree is kind of the ideal object which covers all the k-regular, all the finite k-regular graph. And in some sense, well, you all know now that the expander, that bounding the spectrum is also related to expander. In some sense, that we can make precise, is that the infinite tree is the best expander. Like if you take a subset of it, a finite subset, and you look at its boundary, it's expand in the best way somehow. But we cannot implement the tree in the real world. So if we want to implement in the real world as a k-regular graph, like there are two trivial eigenvalues, k and minus k, which are kind of enforced on us. The k is always enforced on us, it's always. And minus k depends if it's bipartite or not. So in some sense, these are the trivial eigenvalues. And one really have to understand in the general situation what does it mean, the trivial eigenvalues, but they are kind of trivial eigenvalues. And what we want is that all the other eigenvalues, the non-trivial eigenvalues, will be in the spectrum of the infinite tree. That's what we asked, right? The definition of Ramanujan says that either we are talking about the two trivial eigenvalues, and if not, you are in the spectrum of the universal cover. And this is the correct definition of what does it mean for a graph to be Ramanujan. Now, why I say that this is the correct definition? Because last time I also presented to you Alon Bopana theorem. You remember Alon Bopana theorem? Alon Bopana theorem told us that if you want to bound the eigenvalues of k-regular graphs, of an infinite family of k-regular graphs, you want to be able to do it better than this 2 square of k minus 1 for an infinite family. I stress the point, you remember, that for one graph it might be possible. For example, we saw such a graph. What was the graph?
The complete one.
What?
Complete.
The complete graph. Or better and more interesting, the line, we did some computation, right? The line versus points of the projective plane, you remember, the largest eigenvalue was q plus 1, and the others were square root of q, which means that they are less than 2 square root of q. Right? If the degree is k is equal to q plus 1, then I should bound by 2 square root of q. Now, this is not a contradiction, I stress that point. This is not a contradiction to the Alon Bopana theorem. Why? Because Alon Bopana theorem is about infinite family of k regular graphs for the same k. Is it clear? Now, what would be the definition definition of a Ramanujan graph for definition? Or maybe first there will be a definition plus a lemma immediately. Definition: if X is any finite graph, not necessarily regular, and T its universal cover. It's also a tree. That's easy to see that it would be a graph, but a graph which is simply connected is a tree because there are no loops, right? If there are loops, it's not simply connected. right? Universal cover should be simply connected, and it should be connected, and this really means a tree. And then we can talk about, then X is called Ramanujan if all eigenvalues of X are either trivial, so I have to explain in a minute what does it mean a trivial, or in the spectrum of the adjacency operator of T. This is the right definition. Why? Because there is an Alombo-Pana theorem. Alombo-Pana here, well, this is actually a result of Yossi Greenberg. In this case, it's really a theorem of Greenberg. Unfortunately, it's never been, well, actually, in this case, it doesn't matter. It was published in his thesis here at the University 20 years ago in Hebrew, never appeared in the literature, but nowadays in the literature there are more general results than that. So it's already in the literature in a different way, but Greenberg was the one who proved this version. And this is that this is the best bound you can opt, I'll write it in a little bit informally, you can opt for an infinite family covered by T. So it's like, what will be the analog of K-regular graph that we talked before? An analog of K-regular graph that we talked before will be all graphs covered by the same tree, T. In the case, if this tree is the K-regular tree, then the graph, the final graphs covered by it is exactly the family of all K-regular graphs. Now I have any tree. Then I look at all the final graphs covered by it, and they have two trivial eigenvalues. Now, and all the possible trivial eigenvalues, all the others, well, and we call it Ramanujan if the others are in the spectrum of the cover. And I said you cannot get a better bound than that bound. Now, in general, what is the trivial eigenvalue? In general, the trivial eigenvalue is the so-called Ferron-Frobenius. You take the adjacency value, you take the Ferron-Frobenius eigenvalue, and it can appear, and its minus can appear. That's a similar story. So if you know this little theory of matrices, fine. If not, I don't want to spend time on it. But I want to talk about the specific. Okay, the truth is that I'm a little bit hiding. There is a little point if somebody wants to work out a little thesis about that, or check this. There is a slightly, in the literature, there is slightly two versions of the definition of Ramanujan, which not clear to me that they're equivalent. You can talk about the spectrum of that every eigenvalue downstairs is inside the spectrum upstairs of the tree. That's one way to say it. Another way to say it, that every eigenvalue. Now, what is the norm of such an operator? The norm of an operator A is the top of the spectrum. The norm of A is this 2 square root k minus 1. But usually in the literature we say that every eigenvalue is either the trivial one or it's less or equal the norm of A. But I don't think, and I don't know, that for every tree, the spectrum is continuous span. It's really like an interval. what happens, and I think there are cases, even in the biregular, that there is that the spectrum is a union of two intervals. Right? So you can give two different definitions of Ramanujan. One is that all eigenvalues are bounded by the norm of the adjacency matrix, of the adjacency operator on L2 of the tree. Or you can say that you are really inside the spectrum, which would be a stronger property. Okay? So now let's talk about now let now T be TKL. If you take TKL as your bipartite, as your infinite tree, then TKL, the norm of the operator of TKL is equal to square root of K minus 1 plus square root of L minus 1. Which of course, at K equal L, we are getting the old results. By the way, what is TKL? You understand, TKL is the kind of graph that is the tree that the degree here is 3, and now let's say the degree next is 4. And then again, now it will be 3, and the next level will be 4. It's like it's a bipartite. It's a bipartite tree that the degrees are K and L, K and L, K and L, K and L, right? Now, so what is the definition? Okay, so now, well, to be honest, I don't quite remember because it came to me only now when I was doing it. But I think that the spectrum of these three is not continuous. Shachar, you remember? What the spectrum? I'm sure that we looked at it many years ago. What? It's not connected. So in the definition of Ramanujan, you can ask yourself, you can give two different definitions of what does it mean for a biregular graph to be Ramanujan. Right? You can claim that all the eigenvalues are bounded by this number, or they are really in the spectrum. And I'm not sure if this is different. Anyway, what I want to say, that what we found now, so all this was kind of a long remark in order to explain that what we discover now, okay, now let's go, after all this big story, let's go to the example we computed. And I claim that this is Ramanujan. Why? So you see, before that we thought that maybe it's not Ramanujan because the largest degree is q to the 3 over 2. The second one is q, and it's not square root of it. But being Ramanujan for a biregular graph, should be less than this number. So now I claim that this B12 is Ramanujan. Okay, let's check why. Okay, all this was in order to make this claim. Why this is Ramanujan? So let's recall. What was K in this case? In this case, K, it's still written there, I hope. Right? It was like 3 over Q. 3 over 1Q, which is approximately QQ. Right? And N, a Q squared. And
K
N,
and L are written there. They're
What?
the product. Say eigenvalue plus minus square root of K times L.
here they are, right. Okay, so what we need, okay, so yeah, so this is K and this is L, right? So K minus 1, so what we need that the eigenvalues will be less than square root of Q squared plus Q plus square root of Q. That's what we need in order to check if B12 is Ramanujan or not. And the eigenvalues are what? They are square root of this, so this is less than that, and 0. So this is fine, and this is the trivial eigenvalue. So they are Ramanujan. Okay? And the question I want to raise to you, and the exercise, but this is exercise which I don't know to solve myself, and I don't know, I don't think it's a problem for people not to compute, but I have the feeling that if we will look, so fix n, and look at the graph Bij, namely I-dimensional spaces versus j, let's say I less than j, versus j-dimensional, it would be nice to know that they are all Ramanujan. So one should, now we understand what we mean here by Ramanujan. It's taking the degree. To compute the degree, to compute the order of the degrees is not difficult. To compute the eigenvalues is slightly more difficult story. I mean, like, I more or less cover all the trivial cases. Now, well, if I is 1 and j is something, then it's not so difficult. If I think if I or j, I'll give you an hint, or maybe I shouldn't give you an hint. Maybe, I mean, what I think should be done here, but maybe, no, maybe I should, well, maybe let me show you. I'll take another few minutes and then we'll take a break and then you will present your, okay? Let me show you that there is some I mean, we did some trivial calculation, but there is some interesting, not so trivial consequences, which I'm not going to push here, but let's look at the following graph, for example. If I'll ask you directly, then this is I think, a non-trivial exercise, but somehow I think it follows from what we said. Look at the, again, let's look at f cubed to the 4, and let's look at two-dimensional versus two-dimensional spaces, but a different graph than what you think. Well, you don't think, because there is no inclusion. But I want to say, I will connect W1 here and W2 here, connect them by line if W1 intersection W2 is empty, is 0. So if you take two-dimensional subspaces of f cubed to the 4, there are two possibilities. Either they have trivial intersection, or equivalently they generate the full space, or they have a non-trivial intersection and they generate a three-dimensional space. And I want to take one of the two. And so this is a bipartite, not bipartite, sorry. No, this is a graph, sorry. I don't think of it as a bipartite, right? Just, it's not a bipartite, I'm sorry. This is just a graph, like this is the space, these are the points, are the two-dimensional, and I put a line if they don't intersect. Or you can say I put a line if they do intersect, it doesn't matter because it's just a complement. What are the eigenvalues of that graph? That's an exercise that you can deduce from what I said before. And this kind of intersect between spaces, you can start to deduce from the kind of computation I made, and they are needed for solving the more general problem that I presented. So try to play with this a bit. I mean, even partial results would be interesting to somehow. I have a strong feeling that all of them should be Ramanujan somehow. All these type of. Okay, well, I think I talked enough about that. After the break, you will present your solution to the fact that this is a chamber, what we call a chamber complex. Last time, and then if I have time, I will start to do something. If not, I will do next time. We'll go more to the heart of the material of this course. But all this will be valuable for us to get used to take a complex and to compose it to the various bipartite graph, etc.
Showing that there is such a gallery. Now we'll make the proof more aesthetic if we allow the gallery to be something like this. We allow trivial subspaces. Etc. Okay. And then what we want to prove is that well, Alex just reminded us, but I'll say again that every gallery, every what do we call them? Chambers. Every two chambers, V and U, are connected by a gallery. And so, you said what a gallery was, or you remember what a gallery is? Okay. Now, so we first define what the difference between two galleries is. So, two chambers is, excuse me. So we define, you can define functions di, v, u, via dimension of intersection. And let's also define this to be the sum. And we also define the metric to be this. Okay. And now, basically, now that we have this sort of a discrete metric, so all we need to show is that we can do one step. We can take two different chambers and you can make the distance a little bit shorter. Okay? So what we want to prove is that if the distance between V and U is non-zero, then there are two chambers which are sort of neighbors of the original ones, i.e. their intersection is larger than n or equal to n. And the distance becomes small.
V prime and U prime are two chambers.
Yes.
And by intersection, you mean number of spaces which coincide with this chamber.
Right. Yeah. So this basically means that they're either exactly identical or that their intersection is a wall. Okay. So basically we see that these functions, these di are increasing or non-decreasing, and they go right.
Just what is it though? The VU is equal to what? The sum between
The sum of I from 0 to n minus 1, n plus 1, and n.
But sum of what?
Of I, sum of I, sum from I.
You should take it in brackets.
Right.
I mine?
No, no.
No, this is.
Ah.
Exactly.
So to prove this, So, sort of easy observation is that if the distance is larger than zero, then there is an I such that okay, so the sequence has to be constant a little bit, and then it has to increase. And so we can pick some vector which is in the intersection here and not in the intersection here. So pick some W and VI plus 2 intersection VI plus 2 minus VI UI. And then basically what we do is that we just, what we want to do is we add W in the I plus 1 dimension. Instead of, we replace VI plus 1 with VI and W. Okay, right there.
I don't understand something. What is V prime intersection? V is greater or equal to what?
N.
What do you mean by that?
Did I get that wrong? N minus 1. No, N. Right? So we have each one of them has N plus 1 members.
It means that either
You think of it. You think of flag as including also
Also the trivial.
the two trivials.
That's what you.
And there you meant capital G, right?
Okay.
There you meant capital G. Small gi is not defined.
You really mean that they are neighbors, right?
I don't see where you mean.
Here you
Yeah, it's all capital, right? I forgot.
then W is what? Vector?
W is a vector, yeah. Okay. So again, what I'm doing is just, instead of, I replace VI plus 1 with VI plus 1 prime, which, right here, VI plus 1 prime, which contains the I and this vector from the intersection of the higher space. Okay. And similarly, I was replace WI plus 1 with W with U there, right? UI plus 1 with UI plus 1 prime, which contains UI and W. Okay. These are the new. And then, so then V prime is just, it's just, we have this V0, V1 up to V I plus 1 prime, the rest of them remains unchanged, and U prime is the same. And this basically, what this gives us is that the intersections of Vi plus 1 prime and Ui plus 1 prime is a little bit is one larger than the intersection of Vi plus 1 and Ui plus 1. Okay, so this is basically the proof of that. Okay. And so that's it. The diameter. Like what the question Alex asked, what the diameter of the gallery would be, right? That is what.
Why, would everyone understood this point? So maybe illustrate what you're really doing. Like take a simple example like this, the top or the level.
Well, I guess you could say. Well, if you had, say, V0 to V, let's say V1 E1 would be span some vector E1.
So W is a vector, right? We can maybe give it a different name. It
Yeah.
looks like a subspace.
W is a vector, right? I don't know, what different name should I give it? Alpha, say.
What?
Want a different name?
Yeah, right. To stress this is a vector.
Okay. Well, again, you know that at a certain stage, you have two things whose intersection is, say, this. This is at stage I, and stage I plus 1, you know that the intersection didn't change. But in stage I plus 2, you know that it did. Right. So what you do is you just take a vector from here and you put it here. You change the...
What is the prime? No, I don't understand. What is a VI plus 1 prime?
Yeah. So I'm saying, so, okay. Maybe I'll do it slower, okay?
No, slowly and carefully.
Okay. So,
I already saw the proof and I don't understand you now. So
okay, I'm sorry. So, okay, so,
it would be even more difficult for the other.
okay. So we said that there's an alpha which is in VI plus 2 intersection and UI plus 2 and none in this intersection. So we pick. So basically we know that what we know is this, right? Okay, this is what we know, and we just want to. So what I want to say now, this could be either a vector space of dimension I plus 1, or dimension I if alpha is contained in VI, right? And same here. So I just take and the intersection of these two. The dimension of these intersection is larger than the dimension of this intersection because alpha is also here. Right? Okay? So then what I'm saying is that we can pick VI plus 1 prime, VI plus 1 prime, subspaces of dimension I plus 1, such that they are basically here. Okay. And then, so what's not clear? Okay. And then, so we pick. So the chambers we pick are
We change the flag only at one
one coordinate.
coordinate in some sense, and that's really mean that this is you're going to a neighboring chamber because if they agree in the rest of the flag, and the way you change it is such that now we see that there is a new intersection between them. The alpha is inside both of them, so the intersection is bigger than what we had before.
And okay, so I consider this done. Any questions or problems? So that's the size of the gallery that connects two such chambers. So the bound I can say, I think, that it has to be between twice the difference between them and once the between them. But I don't know. I didn't speak about it in terms of n. What is it? N is like the. You said n.
What are you estimating?
The size of the gallery that connects U and V. Okay. So I don't know.
Should it just be the number of basis vectors in which they differ?
Excuse me?
Should it just be the number of basis vectors in which they differ? Just switch one each time.
So what, what's
Yeah.
only?
Wouldn't it just be the number of basis vectors at which the two galleries differ, or not the two subspaces?
You mean what would this be? What the size would be?
No, I mean
Or what this would be?
the distance between them.
Yeah, right. So the distance between them is the number in which they. Right. Okay. So. And
The-
so
DUV is, what is this, at most what?
twice this. So this sort of.
What is it, DUV is at most, what is in the middle? G?
G is the size of the gallery. Which
Ah, size of the gallery.
Meaning the number of chambers.
And at most two, what we call DUV.
Okay, where this part sort of follows from this algorithm.
Right.
We add two chambers and we go down by one.
No?
And the other side is sort of.
And what's the maximum of DUV?
So it's
Sum of ice.
sum of i's minus, well, it's not really sum of i's because the intersection of two large spaces has to be something sort of, right? I mean, I don't know. I checked it once and I forgot already. So now sum of i's minus. Well, we know that the dimension of vi.
Can't it happen that VI and UI do not intersect at all?
Okay, it depends how large, right? If
You look at UN minus 1 and VN minus 1. They are codimension 1, so they must intersect. It's something, so.
So you could sort of use this to find what the number is exactly, but
You can, that would be, but it's a level of n squared, I guess, something like. You can bound it by some constant time n squared, huh?
well, so what is the sum of
What?
The sum of i's is the order of the square root.
There is some steps and whites. So. Okay. Very good. רוצה להגיד משהו? זה אחרת או חשב או חשב? מה? Okay, maybe there is no point that I will start. HANA is a completely different proof, so why don't you show it? It would be nice. There is no point that I will start new material now.
Okay, I provide my induction model. Starting at 3, and then a chamber coming by W1 inside W2, when it is one-dimensional, this is two-dimensional, and we want to pass from this to this. So the gallery we construct is, we start from here, then go to W2 intersection U2 inside W2. Then W2 intersection U2 inside U2. And then we go here.
Just a second, how do you know the W2,
They are of coordination 1, the mass
the
intersection.
W2 and U2, maybe they're equal?
If they are equal, then this in itself is a gallery.
Then what?
Then this is a gallery if they are equal.
Just these two chambers together already.
This is
Two
already.
chambers inside
Okay,
the
and then
one.
we finish. Okay, okay,
Yes.
so, okay, you have to say it. Okay. Either they are already.
Yes.
Okay, fine.
So we get that for n equal 3. This is a gallery, and now assume that for n we have a chamber complex. And now we have two chambers in S and S1, W1 star, which is W11 inside W12, etc. And I. Is 1, 2. And we have to build a gallery between them. So, denoted by Wn-1 E, the intersection of Wn1 and Wn2. So this is of dimension n-1 unless they are equal, in which case we can assume without loss of linearity that they are not equal.
I think you should either switch to Sn+1.
Yes, we are in n+1. Huh?
Yes.
And now, let W3 star n-1 be chamber in SNQ. Any chamber that's coordinate is this. And now, identify W1N with FQN. And using this identification, we can think of, if we shorten this one by 1, it will be a chamber in SNQ. Let's denote by W1 star theta. This is W11, W1, and -1. This is chamber in S and Q. So now we have a gallery from this one to this one.
I'm confused. You had a simplicial complex. All your spaces were in F, Q to n plus 1.
Yes.
So the complex was S n plus 1.
So we take a chamber in S and plus 1.
So A. What you wrote is just n.
This was the injection assumption.
That's the
Ah,
injection.
okay,
So
so-
now we take two chambers in the next level. And if we shorten it by 1, we get a chamber in the previous one. And we have to use an edification of the last one with FQN. So now, by the induction assumption, we have a gallery, let's call it C0 with CR in S and Q, with C0 W1 star tilde and CR is W2. And now we just do the same with the other chamber. We identify W2N FQN, and now you can take any identification. We have to be compatible with this one in certain way that both identifications agree on the intersection W1N intersection W2N, which should be possible. And we have a gallery in S and Q, C tag 0 to C tag S, when C tag 0 is W3, and C tag S is W2 tilde, the short. And now we build the gallery between the original chambers. The gallery in S and plus 1Q. Take the first gallery. And add to each one the W and 1. And then we take the second gallery and add to W2N. And this is just W2. This is W1. And the intersection between two chambers here is a wall because they are different exactly by one coordinate. And the intersection here is CR and C0, which are the same one. with this, we see that if the maximum length of a gallery here is some k, then here it will be 2k, so we get 2k minus 1. But we can do better, much better than that. We can take, instead of taking W3 to be any arbitrary chamber, this one, we can take a chamber that is as close as we can to W1, and then it will be much shorter.
That's what?
We can take a specific W3, and actually you can take the first gallery to be of length n minus 1. Just take the intersection. W3n minus 1 is Wn
Yeah.
intersection Wn1 intersection Wn2.
Instead of choosing it completely arbitrary, you
Yeah.
will choose it in what
So
way?
W3n minus 2 will be Wn minus 1, 3 intersection with W1n minus 1, and so on. And then this gallery will be of length exactly n minus 1. So we get that if En is the diameter of S and Q, then for S n plus 1 Q, we have n minus 1 for the first gallery, n for the first gallery, plus dn. That. So
This
that's
is-
order n squared.
Instead of n square or even n square over 2 or something. You sent me another proof, right? It's a number or it's very similar to one of them?
But I didn't finish.
Oh, I see, I didn't read them, I just thought, okay. Okay, good. Okay, we stop here and next time I will do the